All right, so here we go. NMSI packet, free response, question 1. So we'll go. It says a block of mass M is attached to an ideal spring of spring constant K. The other end, which is fixed, the block is on a level frictionless surface as shown in the diagram. Okay, so it says A. Determine the amplitude of the block's motion. All right, so what we know at this point is this. We can say that because the total energy is going to be conserved here, we can say energy total equals at the amplitude equals energy total where the initial velocity is. So wherever that initial velocity is. So what we can say is that we got the amplitude, we know the velocity is going to be equal to 0. All right, so we can do, that's going to have only potential energy of a spring is equal to, at this point, there is no potential energy of spring because it's at equilibrium and you're just giving it a velocity. So the only thing here is kinetic energy. So if I plug these in, I get 1/2 K amplitude squared is equal to 1/2 mv initial squared. So all I gotta do is solve that for A. I kind of shift that stuff over. K goes over, I get amplitude is equal to the square root of m v naught squared over K. All right. So that's A. Let's clear that. So question 1B. It says on the graph below, plot the kinetic energy of a block spring Earth system as function of time for 2 periods, explicitly labeling any intercepts, asymptotes, maxima, minima with values as appropriate. So it gives us, let's see, it gives us this graph here, like this. This is kinetic energy. This is your period in seconds. I got 2 times a period. This will be 1 times the period. This will be 3. This will be the period divided by 2. All right. So if we're looking at kinetic energy, at the start it says it's given a velocity, maximum velocity. So we got to think about it. Maximum velocity is going to give us our maximum kinetic energy. So that's our starting point. Wherever our maximum kinetic energy is, that's our starting point. So as the block goes, it's going to go back and slow down. So it should decrease. I want to come down here. It's going to decrease at, so half the period. So a period is, it's going to go back, slow down to 0, come all the way back, slow down to 0, and then come back here where it's at its velocity. So if I go at half of a period, I'm going to be back at this point here. In other words, my maximum velocity. So I know I need to get all the way back up here. So I'll undo that. I need to get this graph back up to there. I go back a quarter of a period. A quarter of a period gets me at velocity of 0, so I go back to 0. Oh, that was ugly. I go back to 0. At a full period, I'm back to here, so I'm back at maximum velocity. Half a period gets me to there, 0, 3/4, there. Next is here, 2 times period, there. All right. So if you can just visualize what's going on as the block moves back and forth in harmonic motion, you can just pick points. You pick the maximum and minimums, right? We know the maximum velocity is right here. We know the minimum velocity is at these 2 points. Min, max, all right? So that's B. This is going to be C. It says the block is stopped and a second identical block is glued on top of the first. The blocks are returned to simple harmonic motion with the same initial velocity as before. I guess. How does the amplitude of the motion of the blocks together compare to the amplitude found in part 1? All we have to do is kind of go back to that equation we derived from part A. We got amplitude is equal to the square root of m v naught squared over k. And if we look at mass, right, we look at this variable here. All right. If I put, what does it say, double the mass? Yeah, because we're increasing the mass. So I got 2m there. It's going to go by a factor of 2. So what for part 1, you should check greater than, because the amplitude is going to be greater than, and then this is the proof, right? Oh, this is justify your answer. That's justify your answer. My bad. I kind of justified it first, and then went from there. No, get out. Get out of here. Get. All right. D. Blocks are stopped. The ideal spring is replaced by a nonlinear spring. Will the blocks undergo simple harmonic motion? Why or why not? So the answer there is no, because Hooke's law only pertains to ideal springs. All right. So it's not going to go under simple harmonic motion because only ideal springs all right, that's question 1 done, I think. Is that it? Yeah. Yeah, question 2. All right, clear this up. Question A. So a spring that can be assumed to be ideal hangs from a stand as shown above. The spring constant K of an ideal spring is defined as the force per unit length and differs from one spring to another. It can be measured in both a static and dynamic mode. You wish to determine experimentally a spring static. So this is literally like your lab you're supposed to do. I don't know if you did it or not. Or it's like one of the multiple choice questions we did. So it says, what additional commonly available equipment would I need? So what we're going to do is basically kind of set it up like this. We have this, and then we hang a mass on it, and then we can measure that distance there, and that's my x. So what I need, a meter stick, a known mass, you do a force sensor. Either or, because you just have to know the mass, or you could do a force sensor, because once you pull down on the force sensors, it's going to give you the force and instead of finding mg. All right. So clear that. So this is A. What measurements will I take? Can I undo that? Leave the drawing. So what measurements? So this is number 2. What measurements are you going to take? Well, 1, you have to know the mass, right? So from mass, you can get the weight. You get the weight. Remember, weight is equal to the force of the spring. And then from the meter stick, you get X So you get this distance here. All right, good. And then how would K be determined? So this would be 3. I'll just keep it on the site. Remember, force of the spring equals Kx. Like we said, the force of the spring is going to be up, is going to be down. Because it's not moving, we can do mg equals Kx. And we solve for K, we get K equals mg divided by x. So that's going to be our equation right there. I think that's it for that one, so I can finally erase it. Yeah, so let's clear that. So this is going to be B. So now you wish to determine experimentally the spring constant K of the spring in a dynamic, aka moving situation. What additional commonly available would you need? So for this one, this is 1. You would need a stopwatch and a known mass. All right. We did this. Lab had to do this assigned the other night. So let's see here. That was 4. Let's look at the B. So what measurements would I have to make? Well, obviously you're going to be doing something with the stopwatch. You're going to set it into simple harmonic motion, and then you have to measure the period. So just like we, so set into simple harmonic motion, measure period. That's what you need to do. You need to figure out the period of that spring. And then how would I determine that? I would go here, and I know my period is equal to 2 pi mk, and then I would just kind of solve for k here. I'm not going to, it's kind of convoluted, the solution here. I mean, you can, let me see. Let's see. We'll do it because you have to do it in the next one. So 2 pi, so I get t divided by 2 pi. It cancels out. I get mk. I square both sides. I get t squared divided by 4 pi squared equals mk. I can do this guy here. I get, or I can just, never mind, I'm not going to do that. I'm just going to look at it and know I have to multiply by k and then reverse it. So I get k equals 4 pi squared over t squared. All right, so we'll use that, and then C says, assume that the spring constant is determined to be 500 Newton meters. A 2 kilogram mass is attached to the lower end of the spring released from rest. Determine the frequency of the oscillation of the mass. Well, you have to remember again that frequency is equal to, I'm sorry. I messed it up. Period, how do I do that? Period is equal to 1 over the frequency. So I have to kind of do my inverse equation again. So instead of writing period, the frequency is equal to 1, 2 pi square root of k divided by m. So all I do is plug in. They give me everything I need. I'm looking for frequency. 2 pi. K is 500. M is 2. Do it on your calculator. You should get 2.5 hertz. Right. Pretty easy so far. Pretty easy stuff. let's keep rolling. I guess this is number 3, so let's clear this. So, okay. So what I want to do is, it says in experiment, students are to calculate the spring constant K of a vertical spring in a small jumping toy that initially rests on a table when the spring toy is compressed, the distance from X. Okay, so let's look at initial energy. So when it's at rest on the table, we know that there's no gravitational potential energy, there's no kinetic energy, but there is spring energy. So, right, let's look at final energy, in other words, at maximum height. So, final energy. All right, well, think about that. At the maximum height, it's not moving, so I know kinetic energy is 0. At that point, the spring is not compressed, so it's 0. And the only thing I have is gravitational potential energy, which is equal to mgh. So my total energy final is equal to that. My total energy initial is equal to that. So for the height in terms of m, x, and k. So we want to know the height in terms of m, x, and k, and any fundamental constants. All right, so yeah, so g. G could be a fundamental constant. So what I know is that because there's no outside force, energy total initial has to equal energy total final. So my energy total initial is 1/2 x kx squared equals my energy total final is mgh. Basically, I want to solve for h, so I divide that over. So I get h is equal to kx squared divided by 2mg. My equation for h. All right. So with the spring compressed, the distance of, so you're compressing the spring a distance, so that's going to be your x each trial. The student obtains the following data for different values of n. All right, so it says what quantity should be graphed so that let me clear this. This is B. Should be graphed so that the slope of a best fit straight line through the data points can be used to calculate the spring constant K. So if I look at this right now and I go ahead and graph I'm going to notice that my graph is going to look like something like this. Oops, that was crappy. Let me redo that. All right. So as your mass increases, your height is going to go towards 0, right? As my mass, as you can see, the mass increases, it goes towards 0. As my mass decreases, the height goes up. All right. So that should make sense. And remembering from your linearization data stuff, so to linearize this, what we're going to do is we're going to do an m inverse h graph. So what I should add to that column is and then you could fill in the rest. You know, basically you're just doing the inverse here. So I got 2.0, 2.9, 3.6, 5.3, 5.6. And that corresponds to the ones you already have here. 0.02, 0.03, 0.04, 0.05, 0.06, 0.8, 0.19, 0.18. All right. So that so your answer there is that is what we're going to graph. Then the next one wants us to actually graph it. really what they're looking for here, let me erase some of this. Well, actually, yeah, let me erase some of this. For here, something like this. So this is going to be 1 over h. This is going to be my mass. I got to get like a scale here. If I do by 0.1 each time, this is going to be 0.7 up there. I'm not going to fill in the rest. And I can go up to 6. 1, 2, 3, 4, 6. That's 1, 2, 3, 4, 6. If I look here, I got 2, and mass is 0.2, so I go here, up. I go, what's next? 2.9, so almost 3, and I got 3. I got, next is 3.6, so halfway, and where am I at? 4, 3.6 and 0.4. 5.3 and 0.05, 5.3, 0.05, and then 5.6 and 0.6. So I can draw my best fit line. As you can see, linearized. No, shut up. All right. So from that graph, I'm going to clear this stuff over here. Up. All right, I'm going to look here, draw. So this is D. Slope. I can do that by taking just points I use, 0.06 minus 0.02. That's your vertical, so that's from the, this is from the Y. The X over here is going to be 5.6 minus 2. I got that for my X values, and I get it to be 0.011. Right? Right, because kilograms is your mass, that's in the Y, so it's already on the top. And then on the bottom, you got 1 over meters, so I can just flip that meter. So there's my, that's where my units are kilograms and meters. That's it. Oh, so I need to find K. So I got to find K here. All right, so when did I find a equation for K already? No, I have an equation for height, right? So my height, let me clear. I gotta get some room here. Clear. All right. So I know my height is equal to K x squared to mg. We did that last time, right? So let me solve that for K. I'm gonna get K equals H2mg all over x squared. Right? That's my equation for K. Look, what do I have here? I have, right here, I have kilograms and meters, right? So kilograms is mass, height is in meters, right? So this value here is going to take place of those two. So when I plug this in, K equals 2 times G, which is 9.8. H times G, which is left, is 0.01. 1 over x squared. Well, our x was, what was it? It was, it compresses 0.02. So 0.02 compression every time squared. I can then calculate that. I get 539 meters. All right. So that's D, that's E, clear, clear all, E. Procedure to find the height and experiment given the toys only momentarily. So one, you could set up a meter stick here, a video camera right there. Watch the toy go up, and then you can do that. Or you can measure the time up, right? So if I measure time up, I know velocity final here is 0. I know gravity is negative 9.8. You can use your kinematic equations to solve for your delta y. Is that it? That's it. So if you guys enjoyed this, again, it's the first time doing this, definitely getting better at it. So there you go.